Well, this is the final example we're going to look at in this section on polynomials, and we're going to evaluate or analyze, I should say, the graph of this function right here. So the first thing we want to do again is we want to determine the end behavior. If you notice that this polynomial we're looking at is already factored, and in order to determine the end behavior, I'm supposed to be determining whether or not it's an even versus an odd function. Well, I don't really want to expand all of this right here because that's going to be a really large, ugly polynomial. So one of the tricks that I can do to just determine what the highest exponent is going to be out of this thing is, let's just pick out x cubed, each of these variables. X cubed, here if I were, I have x to the first squared, which gives me just x squared. And then finally I have x squared, because x squared to the first is still x squared. Now, what happens when the bases of my exponents, the bases are the same? What do I do to the exponents? You add the exponents. So this tells me that this is going to be 3 plus 2 is 5 plus 2 is 7. If I were to expand this polynomial, the highest exponent in it is going to be to a power of 7. Meaning this is a 7th degree polynomial, or an odd function, an odd function, and the leading coefficient is negative, so it's flipped. So that is kind of the shortcut way of just determining what the degree of the function is, because I don't really think you want to expand out a 7th degree polynomial. Now that we know what the end behavior is, let's look at those x-intercepts. How did we find x-intercepts? Well, we set the function equal to 0 and we solve. So we're going to take the function as it is, negative 2x cubed times x minus 2 squared times x squared minus 9, set it equal to 0 and solve. One of the beautiful things about this particular function is because it's already in its factored form, when we set it equal to 0, all we have to do is set each of these three factors equal to 0 and solve them. So I have negative 2x cubed equals 0, x minus 2 squared equals 0, and x squared minus 9 equals 0. Starting over here on the left-hand side, when I divide both sides by 2, I would just end up with x cubed equals 0, and then if I take the cubed root of both sides, that's still just going to give me x is equal to 0. In the middle, I have a squared term equal to 0, so I can just quickly take the square root of both sides, giving me x minus 2 equals 0, or x is equal to positive 2. Finally, I have a squared term minus 9, so I need to add the 9 to the right-hand side, and then I can take the square root of both sides, giving me x is equal to a plus or minus 3. Now what's the multiplicity and whether or not these things touch or cross, these roots touch or cross? Going back to my factored equation, for the x is equal to 0, we have a multiplicity of 3, implying that, indicating, that at 0 we are going to, because this is odd, we're going to cross. Here for x is equal to 2, we have an even multiplicity, so we are going to touch. And finally, for x is equal to plus or minus 3, which was this guy right here, go back to its factor, which is a multiplicity of 1, and we are then going to cross. So we're crossing at 0 and plus or minus 3, but we're touching at 2. Now let's determine what is the y-intercept for this. So when we do that, we replace all of my zeros, all of my x's with zeros. I can't talk in this video. Negative 2 times 0 cubed times 0 minus 2 squared times 0 squared minus 9. Okay, so 0 times anything is going to be 0, so this whole thing is 0. So we're crossing the y-axis at 0. Now let's go talk symmetry. Talking about my polynomial again, and I'm going to rewrite the polynomial for us down here. It is negative 2x cubed times x minus 2 squared times x squared minus 9. Okay, so I have an exponent here. My variable x is raised to the third power. This guy is going to be raised to the second power, and this guy is raised to the second power, or we could even say it has a multiplicity of 1. So since I have exponents raised to powers that are neither all even or not all odd, so not all the powers are even or odd, that indicates there is no symmetry. So I was looking at the powers of my exponents. This would be a cubed. This one is going to end up being an x squared, and therefore the 3 and the 2 are not the same, even or odd, so we have no symmetry. Now let's talk about the turning points on this particular function. I know that this was a 7th degree polynomial, right? We determined that already. So it will have at most 6 turning points. Now I'm not going to really determine what those turning points are on this particular function, and you'll see why in a second, but I know to expect at most 6 turning points. So I went and I graphed this function in Desmos. Let's look at it real fast. Here it is. It's showing up on the screen. It's my purple line. It's my purple equation that I have. And I zoomed out a lot on this equation because notice that it drops down all the way to way down here below negative 1500. And the reason I wanted to zoom out on it was just to prove to myself that it was indeed an odd function, that I wasn't looking at my calculator incorrectly. It does come down, it is flipped, right? So my end behaviors here, over here on the left hand side where my, not the dot, but the other thing is at, we notice that the end behaviors are opposite in direction, indicating an odd function. Now we do see also, and by the way, I was able to change the window using this tool here, the wrench tool, and I adjusted my window so I could see this bottom curve, and then with my fingers or my mouse I just kind of scrunched it up a little bit further. But that's how you can adjust the window manually in Desmos. Back to my equation. We know that we have intercepts occurring at, whoops, we don't want that. We have intercepts occurring, let me fix that. Okay, we know that we had an x-intercept occurring here at 0, right? It touches at 0, or it crosses at 0, I mean. It crossed at 0, it touched at 2, and it crosses at positive 3, and over here at negative 3, which is what we figured out algebraically. It's kind of hard to see the origin right here, but you can see that that's what it's doing. One other thing I want to note to you is that this is the correct function, but look how many turning points we have. We have 1, and then we have 2 right up here where we're kind of turning, we're increasing and then decreasing, so that's 2. Then we have 1 here at another turning point, that's 3, and we have another one here, that's 4. We only end up with 4 turning points in the function. And you did do it correctly though if you calculated that you have at most 6 turning points. Remember that the turning points, the idea of the n minus 1 is that I'm only going to be able to locate or determine that I have at most, or the most turning points I can have in the function is 6, but I don't have to have all 6 turning points. And here is the function that we are analyzing.